Today we're going to talk about where all the elements came from. Here's a periodic table of all the elements that make up everything that we see around us. So the iron in your blood, the gold in my wedding ring, silicon in your camera. Where does all of that come from? And in telling that story, we're going to start at the Big Bang, and we're going to look at how the elements are cooked up in stars and in exploding stars and how they're distributed throughout the galaxy. So most of the ordinary atoms that we see in the universe are actually hydrogen and helium. 75% is hydrogen and about a quarter is helium, and everything else only makes up about 2% of all the ordinary stuff in the universe. And we think hydrogen and helium were primordial, by which you mean they were made in the Big Bang. So what about all of the other elements? Well, we believe those are cooked up in stars. And this is something that we've only really known for about 100 years. Of course, the origin of the elements have been a mystery for millennia, but we now, from observations made in astronomy, think we have a consistent picture for where all the elements came from. So how are stars powered? I mean, this has been a mystery for a long time, but it was actually Arthur Eddington in 1920s, I believe, who first suggested that stars might be powered by nuclear fusion. So hydrogen atoms fusing together to make helium, and when in doing so, they release an enormous amount of energy. And this is how we believe most ordinary stars are powered throughout their lifetime. So our own sun, all the energy, the light, the power we see from our sun is produced by hydrogen atoms fusing together to form helium. But in about 4 or 5 billion years, the core of our sun will run out of hydrogen, and it will form a core of helium, and at that point, the fusion reactions will stop, the core will contract to form what we call a white dwarf star, and basically the sun will die. But what happens in more massive stars is very, very interesting. It's in the more massive stars that we think helium can be fused together to form the heavier elements. So in a very massive star, for example, when it runs out of hydrogen in the core will contract, all that stuff will compress down and start fusing the helium atoms together to form, for example, carbon. And this process continues. The core will collapse and crunch down a bit more, and then it will start to cook up heavier elements like silicon and oxygen. So here's a picture of what you end up with in the core of a massive star. So you end up with layers, kind of onion-like layers of hydrogen burning, helium burning, a shell of carbon and oxygen and silicon. But then something catastrophic happens when you start to have a dense core of iron. And iron's crucial in this process, because when you try to fuse things with iron, it actually takes in more energy than it gives out by nuclear fusion. So when you get a dense core of iron formed, something catastrophic happens. The core is no longer producing the outward thermal pressure. Gravity is still compressing things in, and so you get a catastrophic collapse of the star. The core will collapse from perhaps a region the size of the Earth down to a dense ball of neutrons we call a neutron star that's maybe only 10 kilometers across. And so this is an enormous amount of gravitational energy is released in this collapse. And it's the bounce back, effectively, from this dense neutron star core that produces a supernova explosion. The shock wave then disrupts the rest of the star. This enormous amount of gravitational energy is released, and the outer regions of the star are blown off into space in a powerful supernova explosion. So in that supernova explosion, that's when we believe the heavier elements are formed. So all the elements up to iron are formed either in a Big Bang or being cooked up in massive stars. But in that enormous supernova explosion, that's when we believe the heavier elements are formed. So elements like gold in my wedding ring, like arsenic, uranium. Hydrogen and helium are basically primordial, formed in the first 20 minutes of the Big Bang. The elements carbon up to iron are basically cooked up in the core of massive stars in these onion-like shells. And then the heavier elements are produced when a star dies in its death throes in a supernova explosion. So Brady, what we're seeing here is what's left over from a supernova explosion. So this is the Cas-A supernova remnant that was observed to explode on Earth in 1680 or thereabouts. And what we're seeing here is a multicolour image produced by combining infrared data from the Spitzer Space Telescope, optical data in green from the Hubble Space Telescope, and the blue stuff are X-rays from the Chandra X-ray Space Telescope. So, and what we're seeing there is the remnant from the supernova as it heats material, as it plows out through the interstellar medium. So what's going on here is that the elements that were cooked up in the star and heavy elements that were produced in the supernova explosion itself are being distributed throughout the galaxy. So this shockwave from the supernova spreads out at velocities of tens of thousands of kilometers per second, and it spreads out all of these elements throughout the galaxy. And I'm going to show you another one. This is the Crab supernova remnant. This was observed to explode in 1054, although it actually exploded more like 6,000 years ago, because it's actually at a distance of 6,500 light years. So at the center of this incredible remnant, there was actually a pulsar. There's the remnant neutron star left over from that supernova explosion. There's an object in there spinning at about 30 times a second, and that's the remnant core of this supernova explosion. That thing is this is about 12 light years across. So in just 1,000 years, essentially, this thing has spread out over an incredible distance. So to travel at the speed of light, it would take you 12 years to get from one side to the other.